Hi, in this video we're going to take a look at how equations of lines can have different forms and basically have the same meaning. So let's take a look at this equation here. We've got y equals 4 minus 3, or 1 over 3x, and that's in the form of y equals b plus mx, or it's the rearranged form of y equals mx plus b, where b is the y-intercept. In this case it's 4, so if we look over here we see the y-intercept is 0, 4. And we also see that the slope, or also known as the gradient of this line, is negative 1 over 3. And so if I were to start on this point here and go down 1 unit, so I'm going to bounce down here to 0, 3, and then run to the right 3, because we're always going to be running to the right. So I'm going to go to the right 3, 1, 2, and then 3. And then we see that the point that I land on is 3 and 3. Best I can find it there. And so I've come back to, I found another point on the line, starting from the y-intercept and then counting out the slope. Okay, so that's the form where the slope is a fraction of 1 over 3. Now what happens if I were to multiply every term in this equation by 3? So what if, like we've done in the past with solving equations and rearranging equations, I do the same thing to both sides of the equation. So in this case, what I like to do is multiply by 3. And by multiplying every term by 3, what effectively I'm doing is I'm removing this fraction of 1/3, because 1/3, or negative 1/3, multiplied by 3 will give me 1, or negative 1, as the coefficient of this x. And so if I multiply everything by 3, I get 3y plus or equals 12 minus x. So I've just multiplied every single term by 3, maintaining balance in the equation by doing the same thing to both sides of the equation. So look what happens to the line. So carefully look at this red line, and I'm going to turn on this new equation. Notice that the new equation is on the same line as the first equation we had. Is exactly the same thing. Because we multiplied everything by the same number, we multiplied everything by 3, we haven't changed anything because we kept the balance of the equation. Okay, so now what I'm going to do is I'm going to now rearrange this equation, and I'm going to add x to both sides of this equation, 3y equals 12 minus x. So if I add x to both sides, I see this negative x plus x on the right forms a 0 pair, and we've got x plus 3y on the left, and so that gives us this equation down here, equation number 3, x plus 3y equals 12. So if I turn this one on, so take a good close look at this line again, the line that we have. If I turn on this line, equation number 3, I see that the equation, the line, is exactly the same as the second equation, which is in turn the same as the first equation. So I've changed this form around quite a bit, and it's the same line, because it's effectively the same equation. I'm just doing the same. I'm applying the similar operations to both sides of the equation, thus maintaining the balance. And then if I want to do one more thing, if I want to take this and take this x plus 3y equals 12 and multiply, just for fun, I just want to multiply everything in this equation by 5, I would get 5x plus 15y equals 60. Okay, so take another look at this equation. As I turn on equation number 4, we see that it's exactly the same equation one more time. It's exactly the same line. So here we have 4 different forms of the equation, and it has exactly, or it's the exactly same line. And actually, I'm going to do one more step here. What if I were to do 5x plus 15y minus 60 equals 0? Well, there again, we've got exactly the same line going through the same y-intercept. And if you happen to notice before, the x-intercept always was 12 and 0. the whole time. So this line has never changed, even though the form of the equation has changed many times. So this will allow us to set up how we're going to be able to solve equations algebraically. So we'll be able to manipulate the equations without having any, without changing the equations at all. We can just multiply any number through here and we get the same equation. If I wanted to go one more step further, if I take equation 3 here and multiply it, say, by 2, I get 2x plus 6y equals 24. And again, I get the same equation, or the same line that's going through the same x and y intercepts, but it has a different form of that equation. Okay, I can even turn it around. I can do 24 equals 6y plus 2x. And again, the line is exactly the same. Okay, the line's the same. Equation, well, it's not different. It's just turned around. So that just shows you it's the same thing. If I take equation 3 again and just multiply through by -1, negative x minus 3y equals -12. Again, I'm going to have the same line going through the same x and y intercepts by taking this equation and just multiplying through by -1. And I get exactly the same line, which means that this equation is the same as this equation. Okay, well, it's a different form, but it's the same linear relation. Okay, so equations can take on many different forms, and you can multiply by all kinds of different things. As long as you multiply every term in the equation by the same thing, then you'll get the same relation and you'll end up getting the same line. Okay, so that's one thing that I want to take a look at, is just multiplying through by different values to get the same equation. If I go here and open up this other graph here, here's another equation of a line, and this equation is y equals 3x plus 2. So it's in y equals mx plus b form. And here we see that the y-intercept is 2. Okay, right here. And if I were to count out the slope here, so the slope is the intercept, or sorry, the coefficient of x, and that's a whole number, so it's 3, which means it's actually 3 over 1. So the rise is 3 and the run is 1, and we always run to the right. In this case, we're rising 3, and that's positive. So from this y-intercept, I'm going to rise up 1, 2, 3, up to 0, 5. And then I'm going to run to the right 1 and get back on the line again. So there's a point that's on the line, which is 1, 5. Okay, so I've got back on the line after starting from the y-intercept and counting out the slope. Okay, now what I'm going to do is I'm going to turn on a different line. So this is not going to be the same line, but I'm going to turn on a different line now. And we see here is the line y equals -2x minus 8. We see that the y-intercept here is -8, 0, -8. And coincidentally, its x-intercept is -4, 0. Okay, that's just a side note. And notice that these two lines have slopes that are not really opposite slopes, but one is positive, one is negative. So the first line, the red line, has a positive slope, and the blue line has a negative slope, which means that they're going to intersect. And in this case, they intersect at the point -2, -4. Now, what happens if I were to take these two equations and find this equation here? What would I do to these two equations, equations 1 and 2, the red and the blue equations, to get equation 3? Take a look. If we look down vertically, what would I have done to equations 1 and 2 to get equation 3? Okay, so notice that y plus y gives me 2y. And on the right side of the equation, I've got 3x minus 2x. That gives me 1x. And then plus 2 minus 8 gives me -6. Or 2 minus 8 gives me -6. So here's a new equation, 2y equals x plus 6, or x minus 6. So watch what happens when I turn this line on. Look very carefully here around the point of intersection. Watch what happens when I turn on this third equation. Okay, so that third equation, that line, which is not the same as the previous two, as you can tell, it's a different line altogether. It's going through the same intersection point. So by adding two equations, I do get a different line, but it's going through the same intersection point. Okay, so I get that by adding. Now what happens if, I'm going to turn off equation 3 now. Let's take a look at equations 1 and 2 again. And here's a new equation, or 0 equals 5x plus 10. How would I get 0 equals 5x plus 10 from using the first two equations, y equals 3x plus 2 and y equals negative 2x minus 8? Well, if I take a look at y and y, I didn't add them to get 0. I'd actually have to subtract y minus y to get 0. And then here, the 3x minus, and then if I were to do the same thing again and subtract now, 3x minus negative 2x, well, minus negative then becomes a positive. So 3x plus 2x gives me 5x. So in equation 5, it's 5x on the right side of the equation. And then 2 minus negative 8, which is 2 plus 8. As I look at equations 1 and 2 again, look at the constants. 2 plus 8 gives me 10. So here 0 equals 5x plus 10, and I got this new equation by subtracting equations 1 and 2. Now look what happens when I turn on this equation. Again, it goes right through the point of intersection of the original two equations. So by adding the two equations like I did first to get this line, 2y equals x minus 6, or subtracting the two original equations I got to get 0 equals 5x plus 10, all of them intersect at the same point of intersection. So if I take two lines that are distinct but intersect, and I add them or subtract them, I will get the same, I'll get a new equation which has the same intersection point as the original two. Now, looking at equations 3 and 5 here, I'm just going to turn off the original 2 for a second. Look at equation 2y equals x minus 6. That's this red line here. And then take a look at the equation 0 equals 5x plus 10, which is this equation, the green line. Which one of those two equations would be an equation that I could use to algebraically solve for one variable? If I just had one of these two equations, which one could I solve for one variable? Well, here's a bit of a clue. If I've got 2y equals x minus 6, notice that it's got an x and a y intercept. So algebraically, that would be impossible to determine what the value of x and y are. Okay, but if I take a look at this other equation, equation 5 here, 0 equals 5x plus 10, notice that it's a vertical line and it goes through the x axis at negative 2. So by rearranging this equation, 0 equals 5x plus 10, I can algebraically find the value of x, which is negative 2. And that just is confirmed by looking at the graph of that vertical line. And then from there, what I could do is I could take that negative 2, substitute it into 2y equals x minus 6, and get this point of intersection, negative 2, negative 4. Okay, so that's just a little brief video of how we can take a look at different equations of lines, or change the form of a line to show that they're all the same, as I showed at the beginning. And also, if we add or subtract two equations, we will end up getting the same point of intersection. Okay, so that is the major takeaway for this video, that we can add and subtract equations to get the same point of intersection. And the other thing is we can look at different equations and have different forms of the equations to get the same line. All right, so thank you for watching, and we'll see you in the next video.